During last class, we saw together a few methods for, well, the most common ones, I would like to say, for measuring natural stream flows in rivers and torrents. Then we saw how to measure the water level and convert it into stage data. Is there anything that is unclear from previous classes? All good? Okay. Now we will see a graphical tool that is very, very widely used to estimate stream flows. This graphical tool, it's called rating curve. Do you know what a rating curve is? You've heard of rating curves before. Some of you did, some of you didn't. A few words about that. It's a graphical tool that represents a one-on-one relationship, a monotonic increasing relationship between water level and the stream flow at a given river cross-section. Okay? So, let's suppose this is the natural stream cross-section we are interested in. This is the water level. Lowercase h that you see there, it's the water, how did we call this last class? This is the water depth, okay? The distance between the water surface and the bottom of the river cross-section. Normally, a rating curve is simply a graphical relationship between water depth and discharge. Empirically, this relationship is not linear, and what empirical practice shows us is that the concavity goes something like this. This is widely used because in a river cross-section where a gauging station is located, once this once this relationship is derived empirically, it can be used to obtain discharge values just as in terms of water depth. Okay? So normally, several empirical expressions were proposed in the literature. In Italy, it is very common to adopt for representing rating curves a two-parameter expression, a power law. So the discharge is equal to A, which is a statistical coefficient, times the water depth to the power of B, an exponent B. A and B are constant, and they have to be derived empirically. Okay? If you look at the slide, you see several other formulations, but they all mean the same thing. H star is the stage, so what we call last week the water level. If you recall, water level is always referred to a conventional datum, the stage datum, okay? This is the stage datum, and H star is this. The other term that appears here, H0, is nothing else than the elevation of the riverbed relative to the same conventional datum. So this is H0. So the two expressions are exactly the same. It is convenient to use this because normally stage data that you find published by agencies are water level data, so they refer to a given stage datum. Okay? The last expression you see here, you see a Z star and Z0. Z star is the water surface elevation relative to the mean seawater level, and zeta 0 is the absolute elevation of the bottom of the riverbed. Okay? Is this sufficiently clear? So, how do we derive this expression, this mathematical formulation? How do we compute, estimate the two parameters that are needed in order to convert a water depth into a discharge data? We need to start from empirical data. Normally, the source of information are measurement campaigns, right? The most common one is the area velocity measurement campaigns. You remember area velocity technique? We measure simultaneously the wetted area, A, which is a function of the water depth, and the average velocity. And then we obtain a discharge data. So in order to obtain this curve, normally we start from pairs of water depth and discharge. Of course, measuring the discharge, we saw several techniques. Area velocity was one of them, is associated with significant uncertainty, so you will have errors in the measurements. Errors are typically associated to discharge value, not water level value that we can get with the precision of a millimeter or below. Okay? So this is why the pair of observation are scattered around a mean behavior that we have to get by estimating the coefficient, the parameters A and B. So far, so good? You have any doubt? No? How would you, given a set of pairs, so an observation of water level, an observation of water depth and an observation of discharge. Having a set of them, having several, which means, I want to be clear about this, that operators have to go out in the field and measure discharge and water level once, and then come back weeks later with a different stream flow regime and measure a different water level and a different discharge, and then go out again in a different season. So each one of these points requires a single measurement campaigns that can take hours if the river is large, as we discussed already. Given a set of points on this diagram, another thing I want to point out, the independent variable here is the water depth, okay? Discharge is the dependent variable. Normally we use this expression in terms of water depth. We know the water depth, we want to predict the discharge. But it is very often to represent this data with axis in this way. So water depth in the vertical axis and the discharge in the horizontal axis, simply before water depth is an elevation relative to a point. So it is more convenient to represent it graphically on the vertical axis. So my question for you is, do you have any idea on how these two parameters could be determined from a campaign, or from several measurement campaigns, methods? Do you have any idea? From even different disciplines. So, one thing that is very convenient about the mathematical expression that is used by agencies in Italy, that in most of the cases, unless the river cross-section is very complex in terms of morphology, they use a power law. One beautiful thing about the power law is that it can be linearized rather easily. Okay? It can be converted into a linear relationship. How? How would you linearize a power law expression? with the log transformation. If you apply log transformation here and you apply log transformation here, you obtain something like this. Log of Q is equal to log of this quantity, no? And due to the properties of logs, log of this quantity is log of A plus log of H to the power of B. But to the power of B can be written B times log of H. Okay? So if this is now the dependent variable y, and this is the independent variable x, this is the equation, this is a linear equation between y and x. So if instead of working in a natural space, we work in a log space, so this is log Q, and this is log H, the empirical points tend to be, normally, this is what the empirical practice shows, highly tend to be located in the space with a highly linear behavior. And what you get is that the intercept of this linear relationship is log A. Whereas, sorry about this twirl, whereas the slope of the linear relationship is proportional to B. Make sense? How do you determine B and A then? Or B and log A? What method do you know to do linear regression, to perform linear regression? Do you know any method? Excel, but Excel does something. Excel itself uses a method.
Least squares.
Exactly, the least square regression. Look on this side of the panel first. Why least square? Because for each and every empirical point, you have a residual between the theoretical behavior you are trying to identify and the empirical point in itself. So let's suppose this is measurement campaign I. This is the residual, the error epsilon I. What you can do to identify A and B is to minimize the summation of squared residuals. Okay? If you minimize the summation of square residuals, which is what Excel does, for example, you get intercept and slope. And so you identify one possible best fit of your campaign field observations. Not only that, I don't want to turn this into a lesson on linear regression. Not only that, but based on the statistics of the residuals themselves, based on their standard deviation, you can quantify the confidence you have in your model. Okay? If you add in this log space 3 times the standard deviation above and below, you obtain a confidence band that includes 95% of the cases, meaning that your theoretical equation in 95% of the cases can be in there somewhere. And this is what you see represented here. This is in log space. This is the linear relationship, blue, that we identified based on the observation, and this is a quantification of our confidence in that model. Given those empirical data, we are rather confident in this model, meaning that the confident band is narrow around the model itself. Okay? So far so good? You need any clarification on this, or it's sufficiently clear to you? Very good. So we have a very simple method, an unbiased method, to determine A and B based on observation. You understand very well that the more observation we have, the better our, let's say, theoretical model. The close it will get to the real theoretical model behind the data, which is masked by the error in the observation. So this is why the standardization observatory sets a minimum number of points in order to derive a rating curve. You have to have at least 12 to 15 data points, so red circles, in order to construct and then use, of course, a rating curve. It might seem a lot, even because I stressed out that each and every circle there requires hours of work from the operators. It might seem a lot. Why so many? Because, first of all, what we use and what we need is the rating curve in natural space, not in log space. And when you back transform this into natural space, then of course your confident bounds open up. This is exactly the same model that you get back transforming from log space to natural space. And the higher you go, the wider the bands are. Too bad that in most of the cases we are interested in rating curves for high flow conditions, for floods maybe, and that is exactly where we have the highest uncertainty. Okay, this is why national or regional agencies are required to take a minimum set of observation before identifying a rating curve. I want to provide you with a few additional examples on rating curves derived only on a limited number of observations, and rating curves derived instead using the correct value of observation. Let's say what is set as the golden standard for the minimum number of observations. And I want to place this in the context of precision and accuracy. Okay? Here you have two different measurement campaigns with just 5 observations each. These are 5 observations that are characterized by the same measurement errors. Okay? So, just by means of chance, random variability of the errors, you can go out in the field in a given river cross-section 5 times and obtain this set of points. Or you go out on 5 different situations and conditions and using exactly the same measurement techniques with the same sensors and tools, so same measurement accuracy, you obtain these 5 dots instead. Behind the data, there is the theoretical rating curve, the one in green. The one in green is the theoretical one that nobody knows. Okay, it's behind the data. We have to get there using empirical observation. And we have only these 5 pairs of observation, or these 5 pairs of observation. We use least square regression, that procedure there, and we get, of course, 2 different models, the blue line. Now I'm talking about the blue line, because given the data we have in red, if you fit a linear relationship and then back transform to natural space, in this case you obtain this line. The best fit in this case instead is this line. Okay? very different behavior because errors were different in the two cases. Here you have a situation in which, by chance, over prediction error, so getting, let's say, for the same water depth a higher discharge, over prediction error prevailed. By chance, you were unlucky. Instead of having over prediction and under prediction, over prediction prevailed. Plus, by chance, totally by chance, all your points are very well aligned along this behavior in blue. So you apply that technique, you quantify the confidence bound, and the confidence bound gets very narrow. In that case, your model is very precise. Very precise, meaning that, this is very dangerous, very precise, meaning that you tend to get, no matter what, the same prediction. It's very precise, but the theoretical model, the one you would like to know, because that's actually describe the physics of the water depth discharge relationship, is outside the confidence bound. So this is an example of a model that is very precise but not accurate at all. You have a low accuracy. You would like to be in the bullseye, meaning that you get the theoretical behavior with your empirical model. And if you have a model that is close to the bullseye, you have an accurate model. If instead you are very confident in your model, which can be totally wrong, as in this case, if you're very confident in the model, you have a precise model. Is this sufficiently clear? You've seen this in other contexts, maybe? The other situation is quite the opposite. Now you have, because you planned your measurement campaign not in the right way, two values that are close to zero, close to the origin. And these are totally useless value, because we know from the beginning that a rating curve passes through the origin of the diagram, because when the water depth is zero, the discharge is zero. So going out twice with a very low discharge and very low water level doesn't make any sense, right? Then you have, luckily, some measurement higher up and higher up, but what you see here is that exactly for the same water level, you obtain two discharge values that are very different. And this may happen because of the embedded measurement errors that you have on the discharge value. So, two observations very close to the origin and two observations for the same water level but giving very different discharge value opens up your confidence bound. You're not confident anymore in your model. But in reality, it is more or less as accurate as this other one. Okay, so very low precision, wide confidence bound, meaning you do not even you trust your own model. Okay, so wide confidence bound, but more or less a precision that is comparable to this. And this is the situation as it may go. Having at least 12 to 15 observations corrects these problems. Okay, here you have two different measurement campaigns of 15 observations each. Errors are random, so the clouds of red circles are different here and there, and the confidence bounds are different here and there, reflecting the uncertainty you have in your model. But since you have enough observation, now your empirical model, blue line, matches rather closely the theoretical behavior that you don't know. Okay? So, this is an example of accurate and precise rating curve. This is an example of accurate, actually is even more accurate than the other. How do you measure accuracy? The distance between the model, blue, and the theoretical value, green. So this is even more accurate. It's a little bit less precise. So your confidence is lower, but you don't care once you have some, let's say, once you know that the number of measurement is enough to stabilize your empirical models to the theoretical one. Of course, these are examples in which limited number campaigns, 5 or 15, are compared to a model derived with a huge number of measurements. This is how the theoretical model was constructed, the green line, okay? You have questions? So very, very, very important to have a lot of measurements to have a good rating curve. Rating curve is fundamental because most of the discharge value you find published by agencies come exactly from this process. So setting up a rating curve and then using water level measurements converted into water depth to go back to discharge. Critical aspects. Well, you've seen that the uncertainty remains significant. Because measuring discharge is difficult, and the larger the river, the more difficult it is. So it is very common to have an uncertainty, intrinsic uncertainty in your discharge data, even the published one, of plus or minus 25 to 30%. Very common, okay? We tend to look at discharge data published by agency as if they were the gold truth, but it's not like that. Behind those data, there's a huge uncertainty. Then also, another critical aspect is that you suppose when you build a relationship like this that the river cross-section stays stable. And this is true only if the river cross-section is engineered because of the presence of a structure, for example, or a bridge with a stabilized riverbed. But for natural river cross-section, this is never the case. Sediment and sedimentation and aggradation, so erosion and deposition of sediment, alter very, very may alter very significantly along long-term period the shape of the river cross-section, meaning that this is a never-done job. You have to go out again and update the rating curve periodically because the morphology of the riverbed changes. Okay? So this is why it is so expensive in terms of resources, men and women hour, to have discharge data, because every single discharge data comes after this long and expensive process. Last thing I want to point out, of course it is safe to go out in the field and make measurement when the discharge is not extreme, because otherwise, we said this already last week, you expose yourself to threats and risk. You don't go out in the field and measure discharge when there's a major flood. But rating curves then are used and very important also for predicting discharges in high flow condition during floods. And this is the part in interpolation, and we are interested in using these tools up here, where the model is extrapolated beyond the observed values. And this is the area where the two confidence bounds opens up significantly due to that log transformation, back transformation. Do you have questions? And
I didn't understand this one.
If you are in log space, the confidence bound are two parallel lines, because you simply subtract and add a certain number of times the standard deviation of the error you make. Okay? So the model is a straight line. The confidence bound are two straight lines. But then you do the back transformation. And this is when the two confidence bound opens up. And the higher you go, the wider it is. Okay? So normally you have observed data up to a certain point, in this example of mine, up to 1 meter. But this is not a high flow, a flood flow, an extreme flood occurring, because normally you don't go out in the field and take measurement when it's during a flood event. Okay? So, but once you have a rating curve, of course, then technicians uses them also for high flows, and this is where our confidence bound are wider. Okay? I just wanted to point out this. So sections are not stable. We have a significant uncertainty, very often plus or minus 25% or more, as in the slide. And then also we tend to apply these tools also in extrapolation beyond the observation, which adds additional uncertainty. Okay. I just want to go back to hydraulics, open channel hydraulics for a moment. Do you know this equation, Manning equation? You all know it? Some of you don't. Maybe you call it differently in different countries. In Italy, we use Gockler-Strickler, two German hydraulics, whereas in UK and America, they call the very same empirical equation Manning equation. Okay? It's an equation of empirical nature that enables us to have a rough estimate of the discharge water depth behavior even without any observation at all. It's used for this purpose in practice, which is the most common case. Very, very often you are interested in building some facilities, some hydraulic structure in a river that at that point, at that moment in time, was not monitored, is not associated with any gauging station. So you start with ad hoc spot measurement campaigns, but from the morphology of the river itself, you can already get an idea of discharge values using some empirical equation. A very, very, let's say, used and widely known one is the so-called Manning equation, or Gockler-Manning if you live in Italy, for example. I just want to recall it because it's very, very important, as I said, in engaged condition. So there, on the slide, you have a representation of a longitudinal profile in the condition that we adopt, which are steady and uniform flow conditions. What does it mean? It means that from a morphological viewpoint, your river channel is rather homogeneous, okay? It doesn't change as much on the branch you are interested in, its shape, width, and morphology. And we consider a flow condition which is steady. So discharge is constant in time. Discharge is also constant in space because we are considering open channel flow condition. So due to the mass conservation, if certain discharge enters the river branch, then it also exits the river branch. Uniform flow condition means that the geometric parameter, hydraulics and geometric parameters of the flow do not change along the channel, which is, let's say, a working hypothesis that is applicable when, as I was saying before, the morphology of the river stream doesn't change much. Okay? So uniform flows, it means that the water depth is the same along the longitudinal profile. This is the water depth. H, and this is a given river cross-section. Okay, so this is the water level, this is H, this is maybe water depth in this slide is Y, maybe. So let's use the same notation. This is Y, the water depth. This is the wetted area, which is a function of the water depth. This is the cross-section we are considering. So the equation I'm talking about, Manning equation, enables us, it's an empirical equation that enables us to determine the average velocity. The average velocity becomes a function of the morphology and roughness condition of the river cross-section and the water depth. In this expression that has empirical origin, you see an empirical coefficient n. This is called Manning number, and it expresses the roughness of the riverbed. So the resistance that the riverbed offers to the stream. Resistance may depend on the sediment you have at the riverbed, coarser or smaller. It may depend on forms, dunes. It may depend on the fact that your branch is not straight, but it's winding. It may depend on the fact that there's vegetation on the banks. Everything goes into this empirical parameter n, which is very, very important. Then you see a capital R, which is a geometric function to the power of 2/3. What is this? This is the hydraulic radius. You know the hydraulic radius, how it's defined? It's the wetted area divided by the wetted perimeter. That is also a geometric function that depends on the water depth. So R is equal to A divided by P. Times what? Well, in the theoretical, in the more general theoretical, I'm dead wrong, it's an empirical equation. In the more general equation that works for just steady condition, you should look at the grade of the energy line. But if your assumptions is to consider a uniform steady state, then the energy grade line is parallel to the riverbed, so you just look at the slope of the average slope of the riverbed. S is the slope of the riverbed to the power of 1/2. Okay? Square root of the slope. So given this expression, of course, it's easy to get the discharge that becomes only a function of y, and the discharge by definition is the wetted area times the average velocity. Okay? Normally, natural river cross-section are not like this one. Very compact, narrow and tall. This is common in artificial channels. Normally, natural river cross-sections are wide, much more wide than tall. Okay? So, in a mountain stream, in a torrent, you may have tens of meters as the width and an order of magnitude for the water depth of 1 meter, something like this. If you go down in the floodplains and you look at large rivers, again, natural river cross-section might be even a kilometer wide or more, think about the Po River, and just a few meter depth. So this is why in practice, if we are looking at the natural morphology, river cross-section can be represented something like this, much wider than tall, okay? So this is y, the water depth, and this is width. I will call it like, there's no indication, so I can go like B. With B, much larger than Y. This is very common in all natural streams. Of course, if you excavate an artificial channel, situation is not like this. If you build two levees on the side of each bank, the situation is not like this. But if the river cross-section is natural, this is a very common situation. What does happen in this situation? Well, the wetted area is approximately the width times the water depth. And the wetted perimeter is what? More or less the width plus twice the water depth. So the hydraulic radius is more or less B times Y divided by B plus 2Y. But this is much smaller than this at the denominator. So this and this we can erase. And we can write that the hydraulic radius is more or less equal to the water depth in natural river cross-section. This is why, no, there was an indication on B. You didn't correct me. This is why the equation B is uppercase B in the slide. Okay, so I'm correcting it. Okay, so this is why for very wide river cross-section, Q is equal to what? 1 over N times what? The wetted area, so B times Y, but then we have Y to the power of 2/3, so times Y to the power of 5/3, times S to the power of 1 over 2. Okay? Couple of things I want to point out. This is this is an empirical expression for a simplified riverbed geometry which returns a 1-to-1 monotonic increasing relationship between Q and the water depth. And as you can see, the exponent here is above 1. So it reflects this general behavior, this concavity. Okay? This equation here can provide us with an indication on the discharge for a given value of the water depth for ungauged river cross-section where we do not have any measurement, provided that we can have an indication on the value of the Manning coefficient. Right? Where do we get the Manning coefficient? How can we set the Manning coefficient? If we don't have the Manning coefficient, then we're stuck.
Depends on the riverbed. So
yes, but I have to input a number here in order to apply that equation.
It's from tables.
from handbooks, for example, okay, and tables. A question for you, is that a dimensionless number or a dimensional number?
Dimensionless.
Dimensionless? You sure?
Money equation of the empirical coefficient is dimensionless.
Here I have a discharge, so a volume per unit time. Here I have a length, then a length to the power of 5/3. So I get a length to the power of 8/3, right? And then I have a slope that is normally dimensionless. This is dimensionless. Normally is expressed, when I use this equation, in meters over meters. Okay, that's how we express the slope. So it cannot be dimensionless. It can't not be, because here you have cubic meters per second, and here you have meters to the power of 8/3. So this needs to compensate for this unit difference. Does it make sense? I'm pointing this out because you have to be able to look at this table and get the correct numbers, meaning that normally the table you find report the Manning roughness coefficient for the international metric system. Meaning that time is in seconds and length is in meters. Okay, and where do you find it? In several places. And among these several places, you find it also on your virtuale web resource. So if I go down, I change the modality so that we all see the same thing. If you scroll down, below the activity, you have a section here, references and material for in-depth and independent study. There are things that we still have to address during theoretical classes, but there are 3 entries here that you might want to have a look at. Wikipedia entry, it's written very well and can serve as a theoretical basis if you want to go back to the steady state uniform flow equation. Here you have tables with Manning roughness coefficient. Is it sufficiently large? Should I increase, or it's readable? It's readable. So it's divided by type of channel. Main channel, it's the part of a river cross section where the water is normally present, even in low flow condition. That's the main channel. And see, clean, straight, full stage, no rift, or deep pools, meaning a straight channel. Very clean. So these are values of the Manning coefficient for low roughness conditions. You see an average value, and then there's a fork, an upper and lower, because of course all these values were determined through empirical experiments. So you have some uncertainty. You have also indicated here an upper and lower bound. Then let's go down to the opposite end of this table, this entry table. Very weedy reaches, deep pools. So you have jumps with heavy stand of timber and underbrush. So there's a lot of vegetation, you have jumps, very, very roughness condition higher, and so is higher, the roughness coefficient, 0.1. 0.1 meters to the power of 1/3 divided by divided by meters to the power of 1/3. So keep in mind, these numbers work if you work in the metric system, not with cubic feet per second, okay? Then you have example for mountain streams, no vegetation in channels, banks are usually steep. some reference values, and also Manning values for floodplains, so areas where the water enters only during high flow conditions, okay? So it's not always present there, but you may have part of the discharge flowing through floodplains during floods. And so you expect to have much higher roughness coefficient. Then there are also excavated channel, and the formula is very, very general, so artificial channels, and even, if I remember well, pipes, okay? Because this expression is very, very general, so it works even with pipes. Another resource I uploaded for you is a textbook, very classic, which is open source, but here it's more easy to find, let's say in the Virtuale webpage. I just want to point out a couple of things here too. First, you have a preliminary theoretical part on the Manning equation. So notation and theory about the expression, which is a very classical expression, okay? The interesting part of this handbook is what? This photo gallery in which natural conditions and calibrated roughness condition are associated with picture of the stream, so that you can have a reference, you can have a guide to set this number when you are totally out of observed values. Okay? And these are pictures that are listed in increasing roughness condition. So if we go down, I don't know, somewhere here, you see the presence of large stones, an N value that is definitely higher, or down here a lot of vegetation on the banks and a much higher roughness coefficient. Okay, so there are textbook and resources in the literature that provide you with a guide in terms of which Manning number to use. Do we want to stop for 10 minutes, or we are happy? Okay, let's have a look at her. Let's have a 10-minute breaks, and we will start back in 10 minutes from now. So let's say 12:20, something like that. So before we change it to a different subject, I would like to apply the equation with you to have a practical example of the number it can return. Okay? So what I'm going to do, if Panotto works, it seems to be working fine. So I will open up an instance of Excel. Okay, increase the zoom a bit. And then, if I'm able to, save it to i collegamenti per se scegli tu tutti come sì. Save it to my OneDrive in the shared folder that you can access through Virtuale. So it should be here, and then here. Okay. So let's just have a couple of practical examples. We know that we have to set the roughness coefficient, which is seconds times meters to the power of -1/3. This is the roughness coefficient. Then another thing that we need is the width of the river cross section. Then another thing, and this would be meter. Another thing is the water depth, meter again, and the slope. I don't know what I did. Come back.
Automatically zoomed in a little bit more.
I don't know what I did. The signal went there.
Yeah.
I touched some keys and the signal went just there. So how am I going to revert this? I'm not even a window user, so okay. I think I can do without. I will look there. The slope. And the slope is dimensionless, we said. Right? Then I hope that turning off and turning back on will correct the situation. So these are our data. Let's consider the case of a torrent, a mountain stream. And let's suppose that very difficult to use it this way.
There's something about the over there we can.
Oh, if you can help me.
Yeah, I think so, but I don't know the shortcuts or the from the cast.
I think it went
To just one.
exactly.
Screen.
I'll go to setting. I'll find something maybe, and plus it's in Italian, so.
Maybe the display. You scan.
I have no idea. I used to know very well how to manage this in Windows, but I'm not anymore a Windows user, so you have an idea? Where should I go, Reza?
Maybe you can, under notification bar, you right click to open up the tab. Okay, but to scroll down at the right, okay, schermo, and you click on it. Altre produzioni. This again. They used to be showing just screens over there. Then you can.
Se no lo spegni e accendi.
But that will take 20 minutes.
Yeah.
And then our class will be over anyway. So, let's consider a clean torrent. We saw before that the n value for very straight, very clean, no deep pools could be 0.03. 25 was the minimum. Okay. Then if we're considering a mountain torrent, B could be, for example, 20 meters. Y, let's use half a meter water depth. Slope. Give me a good average slope, please, for a mountain torrent. What could be a sensible value for slope? 0.3 would mean 30%. It's a lot. Because that's an average slope. You don't have to think about waterfalls, big local jump. Average slope, it could be 5%, something like that. 1%, 5% is, let's say, a representative value for a few kilometers of mountain torrent. Okay, so we have this value. The first thing we could compute would be the average velocity in meters per second. Tell me, what do I have to write? Average velocity.
B multiplied by 1.
Let's start in the same order. We have the equation on in the blackboard. So 1 over
0.3
1 over n times
B
b, no, why b?
We have R.
Velocity, average velocity.
Hydraulic radius is missing here.
Hydraulic radius, which is approximately the water depth. So water depth to the power of
5
2/3. Okay, times what?
The slope.
The slope.
0.05.
To the power of 0.5. So this is the velocity, okay? 4.5 meters. We don't need all those decimals, it's a false precision. 4 meters. 0.5, 2/3, and 1 over n. Okay. Then, discharge, which will be cubic meters per second, will be what? How do I compute this?
With the area multiplied by the velocity. The area multiplied by
The area, so equal to. The area is what?
P times 1.
B times S time, sorry about that. Y, then, okay. So it is around 50 cubic meters per second, okay? More or less. 20 meters, more or less 50 cubic meters per second. Now I'm copying this column, pasting it here. To see what the impact is of these different terms, okay? Let's consider now a much wider or not as clean channel. So we know that the roughness coefficient goes up. And we saw high values when we are in the range of 0.06, 0.07, okay? Let's see what happens. 0.06, for example, which is twice as much. Twice as much reduces significantly the velocity and the discharge. Of course, is at the denominator. So if this is twice as much, the velocity and the discharge becomes half. Right? Makes sense? Let's go back to 0.03, the original value, and let's look at what happens if the water depth doubles. If this doubles 1 meter, then the discharge becomes more than 3 times larger. Okay? This is how impactful is the water depth. Because we have to keep in mind that the water depth is raised to the power of 5/3. So very, very, an increase in water depth has a very, very high impact on the discharge. And this is why we build levee. Because by building levee and increasing the water depth, that doesn't cause any flooding in the surrounding areas, by a limited amount, the discharge can increase a lot. Okay? Just wanted to point out this. If we want to have a look at what might happen in a large river instead, just to have some orders of magnitude, let's consider a river. Normally, a river, the roughness coefficient is for the river channel can be this if it's straight and clean, but then you have to consider also the floodplains on the side, and we could increase this number a bit to have a realistic value. Calibrating numerical hydraulic models, I've seen many times values around 0.05. The width could be 10 times larger or more. Let's do 400 meters. Let's consider a couple of meters in terms of water level. And the slope. What could be sensible value for the average slope if we are considering large rivers that flow in plains? What could be?
0.01.
1% is still a slope for a torrent.
0.00.
Exactly, one order of magnitude lower or even less. The Po River near Ferrara, near the sea, it's 1/10 of one per thousand. So let's say that 0.001 is already a nice slope for a large river. The Po River near Ferrara, the city here, it's 1/10 of this, to give you an example, so even slower. It means that if you want to have 1 meter elevation drop, you have to walk along a river for 1 kilometer. Con la virgola, sorry about that. I'm used to points in my computer. Okay. So as you can see, the average velocity is much smaller. So roughly in the order of 1 meter per second, 2 meters per second, and the discharge is high. Here too, the water depth is raised to the power of 5/3. So if we build a levee that is another meter high, and this goes to 3 instead of 2, the discharge that can flow without causing any flooding doubles, okay, by simply raising the water depth by 1 meter. Aside from these considerations, what I want to point out associated with the Manning equation is that the utility of this equation is to provide you with some rough indication on the discharge, and more than that, the water depth discharge relationship when you are in desperate need of stream flow observation measurements. Okay? Do you have any questions on this application, easy application? So let's save. I think it's already saved because I saved this file in OneDrive. I'm still without my screen, so bear with me. It's not very easy to. But it was somewhere here.
Yeah.
It was. I don't remember. It was somewhere here. I don't see it.
Windows key plus P and then
giù nella freccetta qua in basso a destra.
Luce notturna.
Proietta.
Proietta lì, a destra.
Proietta. I was easy.
Control P.
It was easy if it works.
Estendi.
No,
Estendi.
No, estendi, then I have half slide here, half slide there. No. Solo schermo PC. Duplica. In my opinion is duplica.
Yeah. maybe going from solo secondo schermo to...
But nothing happened.
Perché schermo completo.
How do I say enter?
Oh, it should be going.
Should be going automatically. Who knows what happened here? I hope I didn't destroy.
There was an error that shows that the USB is unrecognizable. I don't know what happened.
Maybe there's a cable.
But this is an HDMI cable.
Maybe just unplug it and plug it again.
Right. Oh,
Yeah.
okay, that was easy. That was easy. Thanks for your help. Okay, now that we had an introduction to hydrology fundamentals and we characterized the discharge data we will consider the most, the data which we will consider the most, and also had an idea on the uncertainty of these data, intrinsic uncertainty, and how difficult it is to let's say, get them, obtain them. We're moving to a more operational part of the course. We will be addressing in this part of the course a very classical way to summarize stream flow regimes in hydrology for natural streams. This classical way is actually a graphical tool. It's called flow duration curve. I don't know if you have an idea of what flow duration curve is. We will see some definitions. We will start with some definition. We will see how to construct them when we do have discharge data for the river cross-section we are interested in. We will see how then we can use these graphical tools in order to have a graphical approach to common water resource management problems, included sizing of run-of-the-river power plant. But we will see examples of different application to water engineering of these curves. And then we will close this topic by looking at methods. We will see one in particular to predict this fundamental graphical summary of the stream flow regime for river cross-section where we do not have any observation. The practical activity we will perform in the first one, we will focus exactly on these 2 points. When you have data, how to construct flow duration curves according to the definition we have in the literature. We will see there are many definitions of, at least 2 fundamental definitions of flow duration curves. And then we will also try to predict flow duration curve in engaged condition through a regional model. So, flow duration curves, what do they tell us? They describe how much water we have and for how long. Have you ever heard of flow duration curve before? This is the first time you... For all of you, you too, you had some hydrology courses in your bachelor program? You did?
Yeah.
So, basically, what a flow duration curve is a representation of the percentage of time, also called duration, a given stream flow is exceeded over a given period of observation. We have 10 years, for example, of observation, and over these 10 years of observation, we want to represent the percentage of time during which a given discharge value is exceeded. This is time in our conventional meaning, chronological time, and this is a representation of the stream flow during time. The name of this diagram is a hydrograph, okay? And if this time interval it's a long time interval, let's say several years of observation, what the duration is still some time, but it's not chronological order anymore. The duration of a given stream flow is normally expressed in dimensionless terms, so it's a percentage of time over the original time window for which a given stream flow was exceeded. Okay? So if we focus on this stream flow, we see that across this long time interval, this value was exceeded for this duration. Whereas this value of stream flow was exceeded twice, and so the duration is the summation of segment B and C. Whereas the minimum flow was always exceeded or equivalent. And so the duration is the entire time interval we're considering. But normally, as I said already, duration is expressed in dimensionless terms. So flow duration curve can be looked at using two different perspectives. For a process-based or deterministic hydrologist, the viewpoint is an ID, a signature of a given catchment with a given climate. It's a summary of a stream flow regime that reflects particular morphological condition and climatic condition of the catchment and geological condition of the catchment. Whereas if by training you are a more statistical hydrologist, well then a flow duration curve is nothing else than the exceedance probability of a stream flow. Okay? First viewpoint, deterministic hydrology viewpoint. Here on this diagram, you have three different flow duration curves. Okay? We will see this in more detail, but usually flow duration curves are represented on log scale vertical axis, and then the duration, here you see on the horizontal axis. Here you see an altered scale. I don't want to go into the details of this. Let's consider a duration that goes from 0 to 1 or 0 to 100%. It's the same, okay? And these are three empirical flow duration curve for three different streams that we can compare because, so we can put them on the same diagram because what is represented here is not the discharge, but if you look at it, it's the discharge per unit area. So maybe these catchments have different areas, but we can plot on the same diagram the three flow duration curves because we standardize the discharge times the area. Okay? And we make this comparison. They look very, very different, the one to the other. So what is the most striking feature? In what terms these three curves are different the most, in your opinion? What is significantly different in these three lines on the diagram? Say it again.
Discharge?
No, the discharge is here. I heard that the slope, right? Can you see that the slope of these three curves, it's extremely different? So, flow duration curve can be very steep, and that's a sign of the fact that the catchment cannot store water for a certain amount of time. Maybe it's a very impermeable catchment, so you have discharge when you have rainfall. You have limited discharge when it's not raining. Okay? This results in a very, very steep flow duration curve. The stream flow is high only during a limited amount of time when you have the catchment fed by rainfall. And the catchment itself doesn't have any storing capacity. Whereas, on the other hand, your catchment is very pervious, so sand deposits. Part of the rainfall occurring over the catchment flows as a runoff towards the outlet, producing high flow. But a significant part of the rain volume gets into the sand deposits and it's released slowly in time. Okay? So if the catchment has this power of holding some water volume and release it in a much longer time period, as a result, the flow duration curve will be much more flatter, okay? Like in this case. If you see this catchment here, Wapaka River, thick sand deposit. Instead, the opposite end, the red one is the Rib River, runoff dominated. It rains discharge. It doesn't rain, much lower discharge. Being permeable is not the only way in which a catchment can store water, can hold water. Can you think of other ways?
Depth of the...
In which a catchment can store some atmospheric water for a longer amount of time and release it to the catchment outlet across longer period? Ice and snow. Very well. If a catchment is snow or ice dominated, during winter time it holds a lot of water, then it releases during summer and spring. You will see also in that case a very flat flow duration curve. So first and very prominent feature of these curves, how steep they are. If they are very steep, our catchment cannot hold water. If they're flat, it's a catchment that can receive water as rain-fed and hold it for a longer amount of time. Statistical hydrology viewpoint instead. This is the hydrograph up and down. You can see several years in the diagram from 1947 to 1987. I took this picture from a seminal paper by Vogel and Fennessy describing the interpretation of and definition of flow duration curve in the early 90s. So these are the original figures. What I want to point out is that this is the chronological order of stream flows, up and down, high flow season, low flow season, whereas a flow duration curve, it's a summary of the regime that simply represent the exceedance probability of a given discharge. The highest observed flow discharge, this, was observed only during one day, so it has an exceedance probability equal to 0. The lowest stream flow observed across this multi-decadal time interval, this one here, was never exceeded, and so its duration is equal to 1. Okay? You are just representing the exceedance probability of natural stream flow regime. Keep always in mind that for engineering application in which season and chronological time are important, a flow duration curve doesn't tell you the whole story, the whole picture, because the chronological order of stream flow is destroyed, is completely destroyed. You have to accompany a flow duration curve with a representation of the average stream flow regime itself. So here you have several examples. These are all different catchments. You can see that the stream flow regime is highly different. For example, the red one is highly different from all the rest. Why? Because the red one is a snow-dominated catchment in which all the atmospheric water that comes to the catchment during winter months is accumulated, and then during the snowmelt season is returned to the catchment outlet as a snow melt or ice melt, okay? Whereas, for example, you have catchment, the blue one that has snow, but also rain-dominated regime. So you have one high flow season that is here, and it's very different, okay? Anticipated high flow season in March and spring, because it follows the rainfall events. Well, the regime are very different, but the two flow duration curves are very, very similar, okay? The red and the light blue ones. Why? Because they have two different ways, this catchment, to store the water and release water later on. Two different ways, but very similar flow duration curve. So if I'm an engineer focusing on irrigation and I do need the water in very specific seasons and time interval, a flow duration cannot help me entirely. I also have to accompany this information with a representation of the stream flow regime. We'll get back to this. Okay? Is it sufficiently clear? Let me keep an eye on our time. Now, the interpretation of flow duration curve. There are two interpretations in the literature. And they serve different engineering purposes. The first one is the period of record flow duration curve. What does it mean, period of record? It is an empirical flow duration curve that you construct, putting together all the observation you have within a very long time interval. Let's say 20, 30 years of observation that you summarize with a single flow duration curve. This is called period of record flow duration curve. And it's used to make water resources assessment and address water engineering problems in the long term, on the long run. If you want to see your plant, how it behaves, how much energy it will produce in the long run, tens and tens of years. Whereas you may also define flow duration curves on a yearly basis, meaning building a flow duration curve for each and every year you have in your observation in period. So you build you collect the data for a given year and you build a flow duration curve for that year. Then you collect another year, you construct a flow duration curve that might be different. In this case, 76 was drier than 75, so the flow duration curve is lower. No? Makes sense. You perform this routinely for all the years you have in your observation period, and you build 1, 2, 3, 4, 5, 6, many, maybe 20 years, 20 curves. The same 20 years you summarize with a single curve. What is the use of the annual representation? That then you can work on these data to obtain the behavior of, for example, a typical year. I don't know, do you see a black thick line here? This is the median annual flow duration curve. It represents the hydrological behavior of the catchment for a typical year. What do I mean by typical? Typical from a climatic viewpoint, with average rainfall amount. Okay? How do you build a median annual flow duration curve? It's very simple. Once you have your set of empirical annual flow duration curve, you go duration-wise. For example, for a duration of 60%, I look at the discharge value that exceeds 50% of the observation and is exceeded by 50% of the observation. Okay? And I do this duration-wise. If I look at the median, it means that I look at the value that exceeds 50% and is exceeded 50%. But I could also look at different percentile. No? For example, a lower percentile and a higher percentile. These are called percentile annual flow duration curves. This, for example, is the 25th percentile, the red one. What does it mean? It means that it exceeds 2.5 percentile. It exceeds 2.5 observed data and is exceeded by 97.5 observed data. It's a representation of dry conditions. Okay? This is for that given stream, and that cross-section is a representation of the stream flow regime you may have in a dry year, a dry condition. Whereas this one is the 97.5 percentile. It exceeds 97.5% of the observation. And it's a representation of a very wet year, for example. Okay? If you want to look at the situation on an yearly basis, you may refer to annual flow duration curve. So, for example, will it be possible to navigate a given reach of a natural stream in a very dry year condition? You use this representation to understand the duration of time on a very dry year. It will still be possible to navigate a given branch. Okay? We will go back to application very soon, but I want you to understand the definition. Here you put all the observation in a single sample. Here you split your observation period year-wise, and you build one curve for 1 year, and then you summarize these curves in terms of percentage. And I was wrong on the example. This is the 95 percentile, and this is the 5 percentile, but it doesn't really matter. You also have a representation of the variability of the stream flow regime. Within these two lines, the blue and the red, you have 90% of the observed discharges. Okay, so it's a way to summarize the variability of stream flow regime. So wrapping up this definition, and then I'll set you free. Black line here, it's the natural stream flow regime on several years. The red thick line here is the period of record flow duration curve. You summarize all these years with a single line. This is the highest stream flow value observed, this. And this is the lowest stream flow value observed. I would say this. Okay? Or annual interpretation. You see different gray bands describing the variability of the stream flow and what happens, black line, in a typical year. As you can see, the center part of the typical year or the period of record flow duration curve is very, very similar. Differences are within the tails. Because, for example, the right tail of the period of record flow duration curve is entirely controlled by a few years in which discharges were very low. These few years are filtered out. When you take the median, you don't see them anymore. Okay? Clear enough? Okay, on Wednesday we will see how to construct these curves when we do have data, and perhaps it would be good if you can take with you your laptop. Okay? So we have an introduction to R, and we apply theoretical concept in practice through R. Okay? So bring your laptop with you with R and RStudio installed.